Okay, today we're going to go through a quick example using EPOP. The customer is a defense customer that has a legacy diesel powertrain, uh, and they've funded a electric version, but now the objective is to see what a hybrid powertrain, what the size, weight, power configuration of a hybrid might be. So first thing we do is load in a cycle that matches the legacy cycle and add an small electric load too, because the customer also wants to increase the electric export power as part of the conversion to hybrid. So we have the cycles. We then want to go to configuration. Now we have technology, configuration, and the size. So here's the configuration that we're looking at, and each one of these icons has an associated technology which impacts a KPI. In this case, we have KPI of initial costs. So just changing the inverter in this spot here changes the initial cost. Now, what are the sizes of the components? Well, we actually don't know the sizing because it depends on the configuration and the technology. So what we do to make it more intuitive is to solve for every size of battery and internal combustion engine, anywhere from 0% battery all the way up to a full BEV, because there's going to be different trade-offs at play in every one of those spots, along the electrification spectrum. So we have the configuration. This is our legacy configuration. We could see that when we did that, the initial cost increased. Now there's multiple factors you want to include in your analysis, trade-off analysis. There's initial cost, but there's operational cost, there's mass, volume, total cost. So you can see the impact of each. So similar there for this application, the initial cost, permanent magnet is a more expensive option. What is typical is to look at the total cost of ownership. And so you have the ability, say 3 times a week for 8 years is going to be the life cycle cost. So this is the life cycle conditions that it's going to use to calculate it. And you can see that those calculations update live. The technologies that you apply come from a library which you have control over here. Here's the library of inverters. You can see there's cost, volume density, mass density, and efficiency. These are all factored into the calculations. You see the motors, batteries, all the components within the powertrain, even down to the transmissions and hydraulic pumps. So you characterize each of these components in the library so that they can be used in your configuration. So what we have here is a legacy, and we haven't even looked at comparison of two powertrains. Where the only thing we've changed is the motor technology. See if we change that. There's a slight difference between total cost of ownership if you change the motor technology. Now, there's different ways to view that difference. Again, on the spectrum of 100% ICE to 100% battery electric solution. This would be the waterfall of total cost of ownership, where it comes from. the delta. But then you may want to be anywhere on that electrification spectrum, and so you can adjust that live and see how the trade-offs adjust. Volume and mass are other important factors to consider. You can see for an increase in battery, you may get a decrease in the ICE. Let's go back to configuration. Let's not just change the technology, but for the hybrid concept, let's consider an alternate configuration. Maybe series plug-in or series non-plug-in. Here's what a series plug-in configuration would look like. And now we're seeing live the impact to volume with that. But there's also an impact to initial cost and total cost of ownership with this configuration. Now we can go in and update any of the technologies. If we wanted to change batteries, you can see how changing that battery technology affected the electrification spectrum solutions. But you can see the slope here initially goes down a little bit faster than it does for the rest of it. Yes, operating costs go down the more you use electricity, but are you able to support the volume? Is the vehicle able to support the volume of batteries as electrification goes up for the full range of the application? The EV conversions that the customer had already done, the volume was too much, so they actually had to cut down range to a third of the legacy powertrain in order to fit the batteries. So we can see those trade-offs, what the volume trade-offs would be if we wanted the same application to be done versus the legacy diesel versus 100% BEV. But what is more interesting is looks like there's a nice sweet spot in volume with this configuration, with this size. Let's look at mass. Yeah, applies to mass too, where you're able to downsize the engine more than you have to upsize the battery. And the total cost of ownership actually sees a decrease in the total cost of ownership. This is where that decrease is coming from fuel, mainly, but you have to make investments in component technologies to get that efficiency gained in fuel. There's different ways to look at it. This is the legacy cost broken up into a pie chart. Let's look at the mass breakdown. As you move along, you can see how the battery grows, electrification components grow to hit this optimum point here. I think that's going to be our solution. Increases slightly in volume. It's best overall. Hybrid. This is the details. This is the sizing details and the resultant cost, mass, volume from these sizing. This is the energy consumption over the life cycle that we defined. So this is our solution.